There we go. Okay, I think we're on. So, how's it going? What's new? No. Please. Now's your chance. As you know, I want to know this. Let's see here. So we have homework due this Friday, finally. I hear that sometimes you have questions that may not like all 3 decimal places, maybe you need 2 or something like that. Often it says. Does anyone have questions about homework? No.
I got stuck on just the very end.
Okay. Let me see it. Let me grab the homework real quick and see if I can. I'm doing this because, number 1, I care about you all. But number 2, I'd like you to, if you do have a chance for questions, if you have a question, most likely someone else does too. This is good for all of us. And of course, I'm clicking indiscriminately again. Where is my website link? There it is. And let me sign in real quick, Katie. My password is 1234567. If everybody wants to see what my account is. It's really not all that interesting. It's the same that you have on yours. Okay, I'm up.
So starting around question 59 really is where I got.
Okay.
Actually, 57.
57.
58 I got, but I think it was an accident.
Okay, 58 you got.
Yeah, I think that was the standard error. It was the standard error in my model, but it wasn't right.
Okay.
But it just happened to also be on the other model.
Okay, gotcha.
Yeah. So when we add in that residual covariance.
Yes. Where are we for that?
54.
54. Yes.
Well, and that's kind of where I got stuck. Well, when we add in the normalized residual relationship.
Yes.
Into the model. That's where I wasn't totally sure. So it was the relationship, I think. I'm sure everyone's making the same conclusion between number 1 and number 8.
Right. Right.
So you do that like 1 till the 8. I couldn't find an example anywhere of like how you build that into even just the correct.
Into the omega.
Yeah.
Okay. Good point. Yeah, there was no example because we never had one in our syntax. But if we go down, let me just go down to the omega code real quick here. So once again, what you'll have to do for that one is put a label on it. So the label, so here's the omega code, or this is, that's the alpha code. Let me go back up. Here we go. This is the omega code right here. So you'll have to put a label by the term. Let me see if I can. We're gonna try doing something here. Of course I left my pencil at home, so I'm using the old-fashioned stylus. We'll see how this works. All right. So it was item 1 and item 8.
Yes.
Okay. So let's imagine we have x1 tilde x8, right, or whatever the item label is. Sorry, this is not good. You put a label out in front, so you might want to call this like cove or something like that, right? Sorry, I can't draw very well here. When you do that, then in the omega function, when you see down here at the bottom in the denominator, which is yeah, I can try. Stop. Right here. Is that better? Yeah. Oh, thank you very much. It's very nice of you. Thank you very much. I also left my cell phone at home today, so I'm feeling very like in the wilderness now. Does anyone have preferably a new iPhone? No, sorry. So yeah, can I just go ahead and give it to me? It's fine. So in the function for omega here, where the residual covariance shows up is at the bottom. So right here, and this is the denominator. Everything after this term right here, this slash, is the denominator. So you'll want to put that label after where you have the error terms, E2, E4, or 6 in this case. So you put a plus, and it'll be 2 times that residual covariance that shows up there. And the reason for that is what happens in omega to make the whole thing work. It's essentially that covariance matrix of all of the unique variances. So if we were to go back over here, there was this. You remember how there was what we call this is the psi matrix, right? That thing. And that what that tells you is it's a diagonal matrix that has down the diagonal has all the error terms, and the off diagonal are the covariances. It essentially makes you sum every element in that. So that means if there's a covariance in the top, it'll be summed once, and then when it gets down to that same spot on the bottom, it gets summed again. Does that help answer?
I don't know if I'll be able to do it.
Yeah.
But I can try, and I can watch back this on YouTube.
Okay, yeah. So let me see if I can. Nope, that's not good.
It's that part right above, like that x1 tilde tilde.
Yes, this thing right here.
Yeah. Where does that go?
That goes into the syntax, kind of where you see the unique variances, or somewhere above where that colon equal term is right here. So here's the colon equal. It'll be above that.
What's in that?
Anywhere, yeah, anywhere up there. So what happens in Lavon syntax is it doesn't have to come in order. You can read it anywhere in there. So like here, I'm labeling all my unique variances. I could have added another one, just another line down that said, variable 1 tilde tilde variable 8, and then we put the label in front of it. Does that make sense?
Before that calculation happens.
Okay, hopefully that works. That's a good question.
I don't know if that will then help me. It was kind of hard because then once you got stuck on it, like
Yes.
building the model, I
Yeah,
really
you
didn't
have.
attempt any of these.
There's a bunch of the other ones that come down. Yeah.
But I think one thing I couldn't figure out, number 54 was
Mhm.
the test statistic for the improvement in model fit.
Okay.
Is that going to be in the omega?
Okay. So the test statistic for improving the model fit, and I don't have my Lou. Maybe you can remember that I'm blanking on this. Is that the test statistic can come in two places? Typically, there's two places where this comes from. One is a model comparison. So if you did the ANOVA function with the model before and the model after, that would give you the likelihood ratio test statistic. The other, and I don't remember if it's that one or the other place for it, in this case, is the Wald test itself. So if you just look down on the output, this test statistic where you'd find the covariance, which would show up, in under the covariances section, should tell you it as well. I just don't remember which one we use for it.
I think it has.
We use the likelihood ratio.
Okay, so it'd be the ANOVA.
Right. We compare the model with all these residual covariance
Uh-huh.
with the model that we suggest residual covariance.
Great.
We use ANOVA function to compare these two models.
That's
And
great.
then we get the test statistic.
Fantastic. Thank you, Lou.
Okay, thank you.
Oh, and one more thing.
Yes.
I saw some codes they put the residual covariance like in that factor.
Mhm.
Factor equals tilde and
Ah.
then variables. And some people put that residual covariance at that first step. So which is not correct position to go.
Right. It has to have a double tilde, and then the label for it has to just not appear anywhere else in the syntax. Does that make sense? So like if you're calling this the word cove right here, you can't use that same label somewhere else. Otherwise, it's going to take the number and make it equal
So
to
that
something
doesn't
else.
go anywhere else.
That's right.
Okay, so I think when I wasn't getting the right numbers from what I thought was the right model, I was like, all right, maybe it needs to go here. Maybe
No, I know. I totally understand that because that's what I would do too.
Okay.
But what's happening on the inside of Lavon, it's sort of, for all the complication and everything for the code, it's sort of stupid. It doesn't realize, it allows you to take a variance and use it as, for instance, a mean, or a factor loading as a covariance or something like that. And so that's what's happening when you label a covariance, but then you put that same label somewhere else. It's going to show up as something that's probably not a covariance, and that's why it's not going to work. The only time that you start to see repeated labels, I'd say the only time, but mostly the only time you see the repeated labels are when we have those parameter constraints that show up like in the tau equivalent model, where we had to equate all of the factor loadings to be the same value. Then the same label shows up on the same line for the factor loading. So if I go down here for the
Your screen is not synchronized.
yes, there we go. Code here. So this is the syntax for alpha. This is the tau equivalent model. You'll see we use the label LP, and it shows up in multiple places. And that's because we've made all of the factor loadings have equal values for it. So that's only once you get to question 59 after constraining the factor loadings equaled, you'd go and put one label after your factor. So you'd have a factor right here, you'd have a factor equal tilde, and then you'd have that same label in front of each of the items. And that will constrain put the same loading in each of those spots. And that's that crazy tau equivalent model that nobody, well, everybody seems to want, but nobody really likes. No, maybe that's not. Everybody thinks they like, but they shouldn't like it. Maybe that's better. It's really not good for you. It's like too much salt.
You want it.
I'm trying to think of something benign, something non-offensive. I was gonna say like too much alcohol. Well, that varies. Salt, though, we can all agree, right? No. Cocaine. Oh, that's good. Well, depends on how much you're used to it. No, I should. No. This is it's being unrecorded. Yeah. Let me tell you, I have not used cocaine this morning. Okay. Other questions about homework? How's it going? Have you all tried it at least a little bit? Is it taking a long time? I'm sorry. But it's sort of like, and so this is the routine practice of like getting you to do something where you know the answer. The next homework will be with your own data. So the hard part with that is you don't know the answer, but it'll be the same type of thing. So you're gonna, hopefully what you'll see between this homework and homework 3 is that the practice effect will pay off.
Are we doing the same thing with our own data for the next?
Pretty much, yeah. Let me grab the homework here real quick. Unfortunately, my head has been, I don't remember any. I'm just a great absent-minded professor these days. Basically, yes, you're going to do a series of analyses using MLR, which is kind of what we said in Levon default. Do a CFA model that corresponds to your hypothesized dimensionality. So for your data, if you thought there was one factor there, you tried that one factor model. And then see how well it fits. If it doesn't fit, try to respecify until you get good model fit. There we go. Then once you're done, estimate omega for each dimension. And give a histogram of your factor score distribution. So we're going to talk about the factor score distributions today. But basically the same. Does that sound? So what you happened here in the data that you're using, these data were real data from like those gamblers that I talked about, and we thought there was one factor, or we're trying out one factor. That's our hypothesized model, and you saw that thing didn't work too well, and so you went and modified it, and somehow miraculously shrunk the number of items down to a good number, and it seems to fit one factor reasonably well, and you're using it. Does that sound? And again, the purpose of the assignment, this assignment is literally the nuts and bolts of dealing with Levon, because it is a pain to deal with, I can admit. Okay, so everybody else is cool then? Awesome. Thank you, Katie, for your questions.
I've got more.
Oh, please, go ahead if you'd like to ask more. No, now's your chance.
I think I need to try this first.
Oh, fair enough.
Two of my questions
Fair enough.
are,
And for the record, Lou and I are both going to the same conference, but that means email, and you can email either of us if you have questions between now and Friday.
Oh, Thursday.
Yeah, sorry. Won't have class for Thursday.
Office hours on Friday.
I won't have office hours Friday, unfortunately.
Okay.
So this is the last Friday that I don't have office hours. So I will have office hours unless, of course, something unforeseen happens. The last planned Friday of not being in town. So, yes, Lou.
So after this class, I'm gonna stay here. So if anybody has questions, you can
Fantastic. Thank you, Lou. Yes, and do try before Friday. The thing about the conference and me is sort of have an interesting conference. My spouse and my son, my 3-year-old or 2.5-year-old, are going to be there at the same time. So I at one point may be in front of a computer or maybe running after a little guy. So, but I will tell you, if you email me by Thursday night, I can guarantee you getting responses. The question will be Friday. So just okay. Yes. Pardon?
Could you talk about the
Question 60, yes. Question 60, what is the predicted response for item 6 with someone with this factor score of 2? Okay, to do question 60, we go back over, we have to sort of remember what the definition of the factor model is, right? So for question 2, so this is like x2, what does the factor model say x2 should be equal to? What's the model equation? I'll start. U2 plus error, right? Well, the predicted response is given right there. And you know what the factor score should be. It's 2 for value of 2. This is item 6, excuse me. These should be 6s. My apologies. So what you need to do is then plug in the intercept for item 6 and add to it the loading for item 6 times factor score of 2. And that should give you the predicted response.
So we don't add the error in?
No, because you don't know what error is. Right? So for a person with the factor score of 2, it's this hypothetical person. We never know what that is. Besides, not only that, the prediction response is always the part that doesn't include the error as well. And if I go back to regression for just a little bit, because I'm trying to teach, think about the regression line. If you had x and you had y, in our case, y is item 6, right? And x is your factor. But that regression line is describing that predicted responses for every level of the factor. But conditional on that, it's essentially saying there's a normal distribution around it, right? And that the width of that normal distribution, or the variance of that, is given by the residual variance error. So that's why we don't exactly know what that error term is. We're just saying hypothetically this is what the mean should be, or the prediction should be for someone. Thank you. Other questions? Okay. Are we ready to dive into factor scores? Maybe. Okay, here comes the fun part for me. The diving back to the lecture. So last week we talked about how to knock over your Coke. We talked about the tau equivalent model. We talked about what happens when you see that the model fits. You can say, okay, now I can either talk about the model or I can give people scores. And we came up with these reliability coefficients. One was called omega, one was called alpha. But those were reliabilities for the sum of the item responses. And if you remember from my notes, I derived if we took the sum of all the items and we plugged in the factor model for each of those sums, and we kind of worked out what reliability should be. Well, we all know the factors themselves, or the items themselves, are the sum of the item seems a little bit suspicious, and the sum is suspicious for a number of reasons. But even though people love them some sum scores, I'm going to talk about factor scores a little bit more. And the reason for that is our factor scores are really what we get our information from in almost everything we do outside of CFA. So when we switch over to item response theory, you're going to see this. Your GRE score is built from the same method for factor scores. The factor scores themselves in Lavon, we can actually, there's a function that you can use to get the factor score from Lavon. It's called the F-scores function. I don't know if I have it here. Let me take a look. What it happens to be. Here we go. Actually, this is it's factor scores here. Actually, is what I have here.
It's called
Factor scores. Actually, this is a function I wrote for it. Pardon me. I wrote a function in Lavon to do it, but there's also a built-in Lavon function. So if you go into my syntax above, this is where the iPad starts to break. Quit holding. I wrote a function called factor scores. Lavon has a function that gives you factor scores, but it doesn't give you the standard deviation for each score, or the standard error of measurement for each score. And so I wanted to go and give that to you, and so I created the function here to do it. So there's this snippet of code right here where I create a function called factor scores, and in it I use matrix algebra to figure out what the factor score is. If you're really interested in that, and actually I'm going to show you a little bit of that real quick. I am flipping over here. I'm going to see if I have. I'm going to go back in time, actually. I have a lecture over in my other structural equation modeling class that I didn't actually develop for this, but I want to show you a little bit of it. There's a lecture on, it's called On Scores. which is all the way down here. Yeah, and I'll bring this back later in the class when we talk about, ultimately we get scores when, for several reasons. If we want to tell someone what they scored on our test, one reason why we want to have a score. Another reason is we might want to do a secondary analysis. The best way of doing a secondary analysis is the structural equation model. It's a simultaneous analysis for where we don't have to output the score, we don't have to worry about the error that goes with it, we don't have to worry about reliability, we just do the analysis, and the analysis works out well, as long as the model fits. But the sum score itself, let me see if I can find it. Actually, the factor score itself, there's multiple ways of coming up with factor scores themselves. And here's the thing about it. Each of those factor scores sort of follows this distribution. So the idea about the score is that each of the scores that we have in our model, when we want to go and define what the score happens to be, we have to come up with a way of doing so. And the most common way of doing that is a Bayesian method, believe it or not. So what we often do is we look for the distribution of the Go back. I don't believe that happened. The distribution of the factor score given our data. All right, so here all of our items. All right, and using Bayesian, how many of you have taken Bayes? Anybody taken Billy's Bayes? The Bayesian. This is a posterior distribution. We can use Bayes' theorem to re-express this. The distribution of our data given our factor times the distribution of our factor. And then there's some normalizing constant down here, which I'll just leave out. Well, you can show what happens. What this means is that a factor score, each of these parts is derivable. All these things over here on the right-hand side is easily found. I wouldn't say easy, but there's mathematical formulae for each of these. And in a CFA model, these formulae involve the normal distribution. So we're pretty good there. But the concept of the factor score gives us this following chart. Right here, on what you see on my screen here, is that we have, this is potentially 4 different people and their factor scores. And this is a gambling, this is like the data you were using for homework here. Like we could output 4 scores. What we actually are doing statistically when we use this type of method to get a factor score is we're really not getting a score at all. We're getting a distribution for each person. And that distribution represents what their score might be. What's that? It's not necessarily likelihood. It's called a posterior distribution. And so
like the wideness or the dispersion of the distribution would be associated with more
reliability, right? So take a look at this. If we have a perfectly reliable measure, these distributions shrink until they become what we call degenerate, and they have 0 variance. They're just a point themselves, right? So that's the cool thing about it. Reliability for the factor score summarizes how much variation there is in each of the distributions relative to the variation that there is overall for all the scores. Does that sound cool? Just like we're doing, we talked about reliability the last time. What was that quiz item, the reliability formula? Always rho equals variance for the trait over variance total. Right, so that's our reliability formula. Now, what we're looking at here, if you look at each of these distributions, you're seeing a lot of variability, like kind of where their range is, right? That's a lot of variability. How much of that variability is due to where the center of the distribution is versus how much is over the overall there? That's what we're going to try to summarize with the reliability. But in thinking of the factor score, the thing about it is, the key is that when you give a person a number, that again, that's a distribution. You have to summarize that distribution somehow.
So how the individual item play in this? Because
well, let's see where my math is here. You want to see the math for it? Here's the derivation. You can go look up. This is where I taught this much more technically before, by the way. But here, the distribution of the factor score, this is all the derivation of how you get it, using multivariate normals and so forth. But you draw it from a mean that's centered at this number right here, the mean for the factor, times the factor variance, times the factor loadings, plus the covariance matrix of your data, times the distance of y from the mean of the items. So how far a person is from the mean of the items rescaled by how much information each item has for each of the factors, and then put onto the metric of the factor itself.
So it's working with weighted.
Exactly. And so it's a lot of matrices, and you don't have to know the specifics for it. I really don't care that you know them. Quite frankly, I can't get them out of my head unless I spend a long time deriving it. The big picture, though, is that the scoring process for what we do here for factor scores and what we do in almost every other line of work for psychometrics. If you're in IRT, it works this way. If you're in God knows what, it works this way, is that each score represents a summary of a distribution. Right? So here's our distributions. They look nice and normal, but sure enough, not all distributions are normal. All right, so on the left, the distribution is normal, and that means the mean, and the mode. So the mean and the mode, the most likely point and the mean of this distribution are in the same spot. Well, it turns out when your data meet the requirements of CFA, that is, model fits, data are continuous, and not even like enough Likert scale, not even like, yeah, close enough, like literally continuous. When those things happen, you get the shape on the left. You get a truly normal distribution for your factor score. When they're not that way, you might get a distribution that looks like the one on the right. It's this skewed distribution of some sort. It's not necessarily normal. So that's where in other methods you'll see people talk about different methods for summarizing the factor score distribution. The red line is the mean. The EAP, the E stands for expected a posteriori, means the expected value. The M is maximum a posteriori. AP is sort of the Bayesian term. The M is the maximum or the mode of the distribution. What's the most likely score versus what the mean is.
So you can add this from a reliability perspective.
Mm-hmm.
For the normal one, we would say, okay, we would look to things, the shape itself
Mm-hmm.
and the dispersion around
Mm-hmm.
the that shape.
It's a lot harder for the second one.
The second one, is it possible to see, to intuitively to think that there is some bias toward, because it's of the skewness?
Yeah, it's possible. And in fact, that's the thing. It's hard to, the second one, it's hard to get a shape of. We have to use some type of Bayesian method to go get it shaped really well. And how we summarize it now is a subject to figuring out which score to use. But here's the key about it. As the number of items for a factor goes to infinity, right? Think of that as you're sampling from the person. You're sampling something about the person. Then the graph on the right will look like the graph on the left, right? As n goes to infinity, n being an item within a person, that goes to infinity. You start to see the factor score distribution go from non-normal to normal. But again, this second term over here, this is all for things when we're not in CFA land. Right? In CFA land, we pretend everything's normal and we're all happy and it's all good, right? It's the normal facade. So we're going to work with these right now, but when we get back to IRT, we'll talk about these other shaped ones. That's where you start to see different distributions. For us in normal, most people don't even talk about MAP and EAP. They're the same number. The mean and the mode are the same. And they're given by, because we have these normal distributions for the data and normal distributions for the factor, we can do the math to come up with what the distribution of the factor score should be. So that's a factor score. So when I gave that slide, got this picture, and I gave these distributions. I had the talk in Colorado last Friday, and I actually talked about it. And I came up with, I got on the meme generator. Let's see if I can do this here. Let's see if I can show you it real quick. I have my slides in HTML. I'm doing this because I want to show you I'm really more proud of the meme than I am of my talk. So here's our distributions. There we are. I'm saying this because what you have to do is you have to realize there is no score. Okay? So when you look at a distribution of this, when you look at a score for a person, you have to realize that's the summary of a distribution of scores. Seems pretty weird and complex, right? Who's skeptical? Jesse?
I don't know enough to be skeptical.
Has anyone ever told you the score itself is just a summary of a distribution? No. What about when you sum things up, when you add up items together? You get a score. There's no distribution there, right?
Every one of those individual items has.
What I'm going to say is by summing them up, you are implying and putting a very specific model on your items. And that sum score is the summary of a distribution from that very specific model. So that's where I'm going to attack the sum score with. Right? So if you say, look, I can add my items up, what you're actually doing mathematically, we can show and prove that you've just put a very restrictive factor model on your items, one that's likely not to fit. All right? And you're using the summary of that as if it were to fit to describe a person's tendency to have a score. How's that? Who's skeptical? It's okay. This is science. We have to be skeptics. Believe me, I'm a real skeptic.
That's what usually the tests are made.
That's how tests are made. Yeah, the way that, like, your GRE score comes from an EAP estimate right over here. And the longer that you take your GRE, the more items you take, eventually it's pretty much normal. But they never give you the variance for it. In fact, they never talk about it. My spouse made up a slide for the GRE. Speaking of that, if I switch this over, I used her slide about it. Here we go. This is from 2010 and 11. This is the range of error in scores. I showed you this actually in one of our lectures, right? The amount of error in each of the GRE scores. But anyway, these are EAP scores. So I'm sorry. Go ahead.
So that they know that they're based on, wait, you said Bayesian statistics.
Yeah, it's a Bayesian statistic. Your score is a Bayesian statistic. Even if the methods that you do to get the score itself are not necessarily Bayesian, we have to use Bayes' theorem to come about getting the score. Now, there are other methods, like historically, there's been a whole line of research for 100 years on factor scores, and there's other methods out there. But some of the ones that people sort of settled on when people stopped worrying about factor scores, like mainly in the 1970s, are equivalent to what we're doing with the Bayesian statistic. So yes, you're becoming Bayesian. Now, how many of you are okay with Bayes? How many of you have been told don't touch the Bayes? Okay, so that's a big difference because there's some people like, oh, I don't do Bayes, period.
Terrible priors, right?
What's that?
Some don't have terrible priors.
It's all about model fit, right? So we have to have the model fit one way or the other. So let me go back here. Evidently, I've closed my example. But let me go back to the example real quick. Actually, the example was on my iPad. But I'm going to keep the example on here because it's easier to flip around since it's right in front of me. Okay. Going back down to the example, let me go back here. So we can do with the factor scores, we can summarize its reliability doing the same type of a technique that we used previously, right? So before we said reliability was equal to variance true over variance total. Well, variance total we knew was variance of true plus variance of error. That still holds. So the next question is, where do we find all that information when we get our factor scores? And the answer comes from the variance of true is the variance of the factor. Where do we find the variance of factor? Well, if we go back up in Levon, that usually comes from either a model definition, right? We set that equal to 1. There's your variance of our factor right there. Or we estimate it. But either way, that's our variance of the factor. That's how much variability the factor is supposed to have. Right? So the next question is, what is the variance of error? And that's where, when we get down here, the variance of error, well, what we can obtain from each factor is a standard error, the standard error of the score itself. In Levon, again, Levon doesn't actually give that to you, but we can actually get it for us. In my function, I go and use it. All those matrices that you saw before, by the way, I've built into this function itself, so that it should work with any CFA model you use in Levon. All you have to do is pass the Levon object to that function, and it works. But you take the standard error, because the standard error is a standard deviation. What we need to do is square it to make a variance. We take the squared standard deviation, and we get our variance of error. So once again, what we're talking about here, if we go back to my slides from before, if I pull up this model, the variance of the factor is essentially indexed by sort of where the variance of the mean value of these distributions are. How much variation is right where if you were just to draw the means, where would that be? And the variance of error talks about how wide the distributions each of those are. So if the distributions are really tiny, if they're really peaked, there's not going to be a lot of variance of error. And then the only variability you would see for potential scores would come only from the means themselves. And that would be an indicator that you have great reliability for the factor score.
So let's say we have like 3 factors.
Mm-hmm.
We would have 3 scores, or it will be collapsed.
3 scores. Mm-hmm. One score per factor, 1 score per dimension. Just the same way that we would have if we had if you did a 3-dimensional CFA and wanted to sum up items, you'd come up with 3 sum scores, 3 factor scores.
So if one factor has like 3 items,
yeah,
but the other factor has 5 items, the standard error would be different for the.
That's right. They're not guaranteed to be the same. One factor standard error will be smaller than the others, and it depends on how many items, but more specifically how good the items are at measuring the factor. Just the same thing that you'd worry about
But
in.
let us say that all of the items are like 0.7.
Yeah.
But one has 6 and one has 3.
If they're all equal, then the 6 will have better reliability. Same way that you'd see with a sum score. How are we doing? Is this just way off the wall? A little bit? So I don't want you to get bogged down on the off the wall part. The main part is, how do you get a score? If you're going to give somebody a score, where do you get it from? Right? You're familiar with adding together items. What I'm saying to do is, instead of that, you could just use this factor scores function. The factor scores function will give you, for each person in your data set, the score and the standard error for the score for each factor.
Can you quickly go over the syntax here too?
I can do that. What we're doing is we're getting the lav object. This is a Lavon object. So it assumes that you have Lavon already run on your computer. So it extracts the necessary information using this output function. And then I put the information into the certain matrices that I need to make things work. Sigma, model data, and so forth. So sigma is our model predicted covariance matrix. That's lambda psi lambda transpose plus theta. This is that crazy matrix formula that I showed you before. The model data shows up down here. And the scores themselves, we get, this is the factor means. This is your factor, or this is your item variance and covariance matrix. And what was this? I don't remember exactly what that is. Actually, this is item means right here. So that puts those formulae that you saw on the slides, this other set of slides right here, into action. So if you go down to all of this, it's just a mess. Math, words. There we go. So this whole crazy formula right here gives us the mean of the distribution, which is actually the score, the EAP or MAP estimate. And that's where I get this scores function. That's translating that. The other function that the other variance, the covariance matrix that you see here, and this is why I have the hashtag WTF template, which I used to want people to tweet. It's pretty awesome. You can go search it and you'll find it. Covariance matrix comes from, that's what this var scores happens to be. So it's a variance covariance matrix of your scores for each of the factors. We're really concerned about the diagonal of that's your variance of the score, and really the square root of the diagonal is our standard error. So that's where that's coming from. And the rest of it's just a matter of putting it in a data frame that's going to have it factor and the score, or factor and then standard error factor with the label that you used in Lavon to make it show up. So that's what all this other stuff is doing. But all it's doing, if you're familiar with matrix algebra, that's all these star percent symbols. That means a matrix product for what you're doing. So once you have that, though, you can use a function called factor score reliability and calculate how reliable those factor scores happen to be, and you'll see with that your reliability given. And so I calculated reliabilities for both situation P and situation N. These reliabilities that you see here, if you remember what we found in the omega and the alpha reliabilities, alpha reliability was like 0.74, and omega was close to the same, right? Our factor score reliabilities are going to be higher. Why? Now that being higher is an interesting phenomenon, but it's because two competing factors. Number one is to do the factor score, we have to put a prior distribution on the factor. We have to say the factor follows a normal distribution. It's got a mean, it's got a variance, right? We have to identify the scale identification, essentially. So that puts a prior on the scores, which pushes the scores in. They become what we call shrunken estimates. But that shrunkenness that tends to make the reliability go up because it's shrinking not only the score range, it's shrinking the error range as well. As the number of items goes up, the amount of the impact of the prior is minimized, and so you start to see with a lot of items that this reliability for the factors look much like the reliability that you'd get from the sum scores and everything else. So you may call this artificially inflated. I don't think it is, but this is relying upon factor information. Actually, there's another part of this I didn't actually mention before. The other part of this is in the factor scores, there's an added benefit that you don't necessarily get when you use sum scores. And that comes from, scroll up here, this estimated factor covariance. Right? Your factor covariance in a CFA model describes how much you know about one factor from knowing the score of the other. And our factor covariance that we estimated for these data is 0.56. In this case, it's a correlation of 0.56 because they're standardized, right? So what that means when we build the factor scores, that correlation is going to impose itself onto the factors themselves, right? Because you're not creating factor scores absent of each other, we're creating them simultaneously. So that means that when you have a small test, the correlation of factors borrows information from one to inform on the other. It increases the reliability. It's a prior distribution. Here's a thought experiment for you. If you took the GRE, now they don't do this to the GRE, but if they did, but imagine that you took the GRE and they were able to get a better estimate for you by doing a simultaneous analysis of your math score and your verbal score. But there's potentially the case that by using this prior distribution that sort of applies from the entire group, but it may not specifically work for you. Would you be worried about that? So it becomes debate. Where's the limit of prior versus individual information come into hand? And there's no answer for that. But another place where the factor scores are giving you a difference in why the reliability is higher is because it's borrowing information from each of the dimensions. Right? So if you think about it, if we look at this, I know it's really faint here, but this is our path diagram. Each of the factors is directly measured by each of these items, right? So each of these items is providing information for each factor. But you'll note there's another arrow there. And that other arrow is providing information as well. And it's like an indirect. So basically, the items on the other factor are providing indirect information from the factor of interest in this evaluation. And that's fine. That's how it works. That's how it should work. I'm okay. As a Bayesian scientist, I'm okay with that. It's helping us stabilize it. Yes, Shada. I see the sum score regardless, and that drives me nuts. Yes. In fact, I see the sum score reliability reported when people are using IRT factor scores in their analysis, which is ridiculous. In fact, you can go to the GRE Guide to the Use of Test Scores, this thing right here, and you'll see them report a sum score reliability to describe the reliability of their factor scores, which is inappropriate. So I would argue, and I would argue with you, or I would advocate for you, is whatever score that you're using to give to people or in your analysis, you put the appropriate reliability for. If it happens to be a sum score, in just a moment I'll try to describe why I don't like that, but if it happens to be that, put omega. Don't call it omega, call it a reliability, call it good, right? If it happens to be a factor score, put the factor score reliability. Don't call it factor score reliability, just call it reliability. Move on. But it's essentially the amount of variance in the trait, or a total variance that's due to the variance in the trait. It still makes the same thing. So, Jihan.
If I want to compare two groups, I use the distribution of the factors for two groups and like similar to P.
If you wanted to do that, yes. What we're going to show in this class is that's a structural equation model. So the best way to do it is to build in a group variable and to predict that group variable, or use that group variable to predict the factor scores, right? And that will do that. But if you were to output the factor scores, then yes, if you had different groups, that might be a way that you could do it, assuming certain things hold. Lou. That is on the example. Yeah, the factor score, this one right here. That is our example for lecture 4 for our class this year. Right, this one, the factor score function. So yeah, so what you have to do if you want to do factor scores from this is just copy my functions down, put them into your R script, and call them, and you'll get the factor scores. You can even use the Levon built-in function, which is actually called F scores, to get your factor scores and compare them, and they should be the same. But let's go down through the rest of the example here real quick, shall we? What we can do, in the factor scores themselves, we sort of talked about them, and I'm telling you why they're good, but I'm going to tell you a little bit more after I get to this next part. If we were to test the assumptions of classical test theory, we could start by doing the following, right? In this actually, I had debated where to put this section of the example, but really I should probably put it before the factor scores. We did 2 analyses, right? We did one where we calculated for the sum score, the reliability using what we're calling omega. And we did one where we calculated for the sum score, the reliability, which we're calling alpha. Those 2 models one is nested in the other, right? And one of them is called the tau equivalent model, which is the part that gives us alpha. That's the model where we have the factor loadings all set to be equal within a factor. One was sort of the congeneric CFA model. Well, we could use this ANOVA function, and actually, Katie, this is where we can do. Yep. This is how you check whether or not a model fits better than the other. When you have nested models, it gives you meaningful statistics differences. And what it's telling us here is we're going to test these 2 models. We're basically saying the null model in this test is alpha, is the one that's more constrained, the one that has more degree of freedom. So this is the tau equivalent model saying, okay, I'm going to add things up and I'm going to report the factor score reliability using alpha. That's what this model is saying. I can test whether alpha is a valid way of reporting reliability for sum scores. How do I test it? I take the model where I've constrained the factor loadings to be equal, and I compare that to the model where I let them be free. And my p-value here is very small, which indicates that my null model, which is the model that has the constraints, should be rejected in favor of the model that doesn't have the constraints.
But for us, we're comparing the omega estimates. No.
And for homework,
Yeah.
you're going to compare, instead of doing factor loading constraints, actually you will end up getting constraints, but we don't ask you to do the test. Actually, there. Question 63 is this question right here with respect to this model. For your question that you asked in the beginning of class that talked about question 54,
It's the syntax omega compared to the one before it.
it's the syntax omega compared to the model where you've added that residual covariance. So what happened?
Yeah, that's for me. That's the model before it.
That's
Don't
okay.
worry.
Yeah, sorry. Yeah, sorry.
Okay,
Yes, exactly. So you'll do ANOVA there,
Yeah,
and what you should see is one. If I go back to my example output in your ANOVA for that question number 54, you should see 1 degree of freedom difference, and that degree of freedom difference indicates that the model that has more parameters has 1 more parameter than the model that has fewer, right?
So then what you would report there for number 63 or whatever
Yes.
that was,
Mhm.
the test statistic? I
What-
can't remember the actual
what-
language.
Yeah,
that it
let me
asked.
pull up here.
Right.
What is the test statistic for reduction in model fit from constraining the loadings?
So that would be your difference in chi-square.
That would be this chi-square difference right here. That was 63, question 63. And then what are the degrees of freedom for this test statistic? You can find that too, right
That
there.
would be 4.
That's right. So there you have it. So this tells us that the tau equivalent model doesn't fit. What does that mean for our reporting of results? To me, that means you should never report coefficient alpha, because coefficient alpha does not fit the result. Even if you even if you have the same sum score for the data, you should not report coefficient alpha. But we talked about that last week. You shouldn't report coefficient alpha anyway. You just use the omega and call it reliability.
Which is in essence saying that there is no like the item loading is different.
That's right. The loadings, at least one of the loadings is not yeah. That's right. At least one of those loadings is different than the other.
Would it be interesting enough to report both of them and then understand the discrepancy between the two?
No. Sorry. My laugh about that is because usually when you report more, then people are like, that just opens the door for all sorts of ridiculousness. Let me tell you this. What happens is omega, when you have a model that fits the data and fits the data well, then omega will be higher than alpha, and alpha will be higher than when we did the Spearman-Brown version, right? Which is the parallel items model. How much higher they're going to be is almost negligible. It's really tiny when the model fits the data. So oftentimes you wouldn't report both because they're practically the same number.
So if you do report alpha or Spearman-Brown, then it's almost like maybe it doesn't fit.
Yeah. So I would just report one reliability number and also I don't think reliability is well understood. I really don't, because it's why you see it's reliability for what and how. Everybody wants an alpha, but that doesn't apply in most situations. So, yeah.
For either the omega or alpha, you are reporting the reliability for each factor.
Mm-hmm.
But like in this case, there are two factors in this whole
That's right.
Instrument. Or is there overall reliability for the whole instrument?
No, and that's the thing. You have to. If this is a great question, because I often see that too. I have this multidimensional instrument. Here are my factors, and the overall reliability is this. That doesn't fit because you've just established there two scores are needed to describe the data. So there is no one score that you can give someone and then go summarize that by a reliability. So I think ultimately when you build your case for what you're doing with the data, the reliability has to match your analysis, and that means it has to match with respect to the model you used, the number of factors that you have, and so forth. But it's a great question because I often see that. In fact, being an editor or a co-editor of JEM, Journal of Educational Measurement, it's a methodological journal. I just had a series of papers that came through for review that essentially were talking about the overall reliability. And I'm like, it just doesn't exist because it's not there, right? Reliability, it starts asking the question, reliability for what? Right? Well, is it a sum score or not, and how many factors or not? But that's a great question. Okay. The other, as we go down the example here, the last model in the classical test theory that we talk about is something called the parallel items model. This is what gives rise to Spearman-Brown. There's absolutely no reason that you'll ever need this syntax in your life, right? I'm doing this because I'm trying to kill the factor score for you. I'm trying to make it easy for you, all right? So, that being said, what is Spearman-Brown? What are the parallel items? It means where all the loadings are equal for a factor and all the residual variances are equal for a factor, right? And so the omega coefficient that we calculate with the loadings and the variances is equal to Spearman-Brown, and you can see its values get estimated down here, and they're roughly the same also to what we saw with alpha omega before because their model fit the data. But here is why I'm describing Spearman-Brown for you and parallel items, because I'd like to show you a little bit about what happens with our factor scores. Let's take a look here. So let's take a look at the distribution of factor scores for a moment, because I think there's some information to be gained by this. For each factor score, what we get in this analysis is, and this is in using our this factor score function from above, what we can show is the variance of the factor score for the situation positive factor. It's 0.777. Well, you'll note that the variance of the factor score, this is the variance in the outputted scores. It's the variance in the means of all those scores themselves, right? It's like taking a look at this weird graph of the four distributions and trying to describe the variance of the factor based on those means, which is not that you would expect the variance of the factor to be 1 because that's what we're estimating it as. But in practice, when we output the scores, the variance is smaller than 1. The reason for that is shrinkage, right? But that being said, you can still take the standard error for each factor score that comes out of the same f-scores function and produce a confidence interval for where that score should be, right? Because in CFA, it's all normal. Plus or minus 1.96, which I'm conveniently rounding to 2, gives you the score, plus or minus 2 times standard error, gives you a confidence interval for each score. But let's take a look at the interval of scores themselves. This is the interval for the, here we go. This is our positive situation factor score distribution. It's not that unnormal, but it's not quite normal, right? It's not perfectly normal. It's got sort of blips to it and so forth. Right? We can do the same thing with the negative forgiveness. This is a little less normal themselves, right? It's negatively skewed, right? It goes negatively skewed that direction. Yeah, that direction. Okay, so the thing I'm saying this before is because the factor scores from the parallel items model are equivalent to sum scores from the parallel items model when you constrain the factors to be uncorrelated. And here's what I want to show you. So I ran the Spearman-Brown or the parallel items, and I fixed the covariance between the factors to 0. So we know this is going to fit worse because we estimated that covariance to be significant before. And here's some plots. Okay. So here's 2 plots of scores. On the left, you see the sum score for situation P. On the right, you see the sum score for situation N. Those are the the y-axis. On the bottom is the factor score for that respective factor. So situation positive is down over on the left side. Situation negative is down over on the right side. And you'll see there's a very high correlation between sum score and factor score. Right? So you're like, okay, it's fine. And I get that. But if you're providing scores to people, take a look at what could happen. Right? Someone with a sum score of 15, it's possible their factor score is, they have a lower factor score than someone who's has a sum score of 12 or 11 even, right? Look how far down you can go and see how much that might wiggle around, right? So here's the plot that drives me nuts. What is the model that gives rise exactly to the sum score? And that's the parallel items model. Right here, this plot. This plot, the way I formed this was taking the factor scores for the parallel items model when I had uncorrelated factors. And so you see the plot on the left, the sum score and the factor score are perfectly aligned. Right? The plot on the right, the sum score and the factor score are perfectly aligned. The difference between these two graphics is exactly what I was talking about, the scale of the axes, right? Over here on the left, the mean of it somewhere where the mean of the sum score is, on the bottom, the mean is where the mean of the factor is. So what am I saying with that? I'm saying that if you're going to add scores up and give them to people, there's a big chance that you give people the wrong order, unless the model fits the parallel items model. Right? So if you're going to add scores up and give them to people, you may be biasing your results somewhat. Now, it's not a lot, depending on how close the model fits to whatever. But basically what I'm trying to show you is those sum scores that you know and love that you were taught, I don't know how many times and how many classes, particularly in my program, they come from a very specific, complicated model. And that if those model assumptions don't hold, the sum score shouldn't be valid. Right? It's less valid than factor scores. So what do you think? Does that kill it for you? It killed it for me. I don't know if it kills it for you. Why do I want it dead? I don't know. It doesn't kill it. It's not that big of a difference, but it is a big difference if you're thinking about it with respect to a couple things. The choice of model and how well the model fits have ramifications for how the scores look. A lot of times the ramifications are with respect to how much variability there is around the scores, but sometimes it's also with respect to where our score is located. So, all right. I know this is, I'm going to take a drink. Think about it. What do you think? Be skeptical. Tell me why you don't care.
I have a question. If in structural equation model, maybe need a single score as a predictor to predict other factor. So someone will use some score as a predictor to predict other score. If it's multidimensional, what can be the predictor? Two-factor score.
Right, you'd have to have more than one predictor. Yeah.
Actually, for me, I think it goes back to the theoretical aspects, which is the parallelness of the item, and which is very difficult to have.
Agreed.
For item. So.
Agreed. No, and that's the thing. Did you know the whole time that you've done sum scores, you've been doing the parallel items model? Is what I want to ask you first. That's what this is telling you right here. Every time you've done a sum score, you've assumed that.
Same equal.
So the probability that your data is going to fit the parallel items model.
Pretty much zero.
So it's just inappropriate pretty much across the board.
When I look at sum scores, I think the question I ask you if you're going to report a sum score is, did the data fit the parallel items model?
Actually, it's kind of like if you establish the factor score, it will by default, if you have parallel items, it will give you the sum scores.
That's right.
It will fit perfectly.
That's it. That's exactly it. Another step with that, have anyone ever heard of parceling before? So there are a group of people led by one of our former colleagues on campus. I wouldn't say led by, but a prominent member of that group, Todd Little, who used to be part of our colleague set here at KU. Parceling is the idea that you take a set of items and you sum them together, building a parcel. And instead of putting each item uniquely into analysis, you just take the sum of the items and put that in instead. Well, what are you doing with that parcel? Parallel items, right? Well, knowing how, I'm going to be real with you for a little bit and give you my real opinion, unfiltered. Knowing how I've seen this in practice work, is if you can't get your model to fit, it's very easy to get your model to fit by taking the items that aren't fitting and adding them together, and now all of a sudden your model fits, because you effectively reduce degrees of freedom. Why that's cheating to me, and what you should be doing otherwise, is if you want to add your items together, you should be making the parallel items constraint in your model to begin with to do parceling. Right? Because you can. You're only estimating, one factor loading, one unique variance for it. It's a simple constraint to put in, and then test model fit. Yeah.
So I've also understood that when you create these parcels, that they should have, it's ideal if they have an equal number of items in each parcel, like 3 per or like 7 per, whatever.
It doesn't matter, I don't think. The reason why it won't matter is if you put it in another model, it should account for the scale difference, right? So the number of items, so the parcel, if you have 3 5-point Likert scales, the score range is what, 5 to 15, and the same thing with compare that to 7, it's 5 to 35. Well, that scale difference gets absorbed by the size of the parameters in the model itself. So I don't think it matters as much.
So it's more just for like test generation to say that these domains have equal numbers of items?
I would suppose, yeah. To me, what's the more problematic, actually there's 2 parts that are problematic to it. The sum score has error to it, right? Well, I haven't shown you this yet, but each of the anytime that you're outputting a sum score, let's just take a look at this graph right here, right? So you output a sum score, you just create a sum score. It's like going and doing this factor analysis right here, outputting the factor score and then forgetting the error that goes with it, right? It's got an error to it. But if you go put that in another analysis without bringing that error over, what are you doing? You're saying I've got great reliability, perfect reliability for that parcel, that sum. So that's problem number 1. But problem number 2 is model fit. Right? When you sum up those items, you lose the ability to detect model fit for the items that you're summing, and you can't test it uniquely. So in my world, if anybody does parceling, what I will ask for is, okay, parcel, fine. That means you have to test this parallel items model for each parcel. You don't need to add them up, just put them in as is, just constrain their factor loadings and unique variances to be equal. Nobody would do that, because it would never fit. Exactly, and that's the reason why parceling exists, because it gets around the goodness of fit. That's my unbiased opinion on it. Actually, it's biased, but I'm biased from the it's cheating. It's cheating. That's how I want to call it. When I see parceling, I say I'm hiding model fit. I've got something to hide with my data. Does that sound strong? Bad?
No, I'm excited because
Have you parceled before? I don't want to. You didn't know.
I have a parcel before.
That's good.
But I worked on an assessment that does use parceling.
yes.
So I'm
Was
learning
Todd part of
about
the
it.
authors?
Mm-hmm.
Uh-huh.
And learning about it and trying to understand. So it kind of helps to understand that those are how the items that they're just one parcel. That's what it means.
Mm-hmm.
But I guess now it makes me skeptical when looking at like the model fit tables.
Mm-hmm.
To be like, well, what does that even mean? Or like, how many times has it kind of been worked around
That's
to
exactly
get
it.
that number?
That's exactly it.
So that's why I'm kind of excited to see what outcomes
Mm-hmm.
from this class then.
Yeah,
because
when you do the
that's-
other homeworks with your data. Or,
Yes,
Mhm.
yes.
Yeah, I'm excited for it too. I'm excited because, so this is really interesting. I'm at this conference I'm about to go to several years ago. Not Todd, someone else, gave a talk on this subject on parceling. And I went up to them at the break. This person shall remain nameless. And I asked this person, he or her or she, isn't that just, I called it the tau equivalent model. And the person, I don't know how to describe it, I touched on something that enraged them so much that they became flushed and started yelling almost. And I was going with, hasn't this ever been thought of? Because when I read the parceling people who are parceling, nobody ever talks about this. But you can go and show it. If you're going to sum up the items, this is what you're doing. You're essentially assuming the factor loadings are equal for them and all the residual variances are equal for them. And then you're going to put them in a model.
So,
Yeah, and that really was really traumatic. It was like, wow. Anyway, yes, sorry, Mayumi.
Well, anyway, it's kind of like my assessment specific,
Mm-hmm.
but
Yeah, it's fine. Please, everybody's going to have a question like that. It's great.
because that's the assessment is made up,
Mhm.
being reliable. But so the items I believe in.
Mm-hmm.
How can I?
Reassess it. I would go with whatever you're summing. Try to put a model on, or try to put a non-parallel items model on, because it may fit. It may do fine. You may find it. My hunch is it probably, when whomever did that probably found it didn't fit and wanted to keep the items, and so the way around it was, all the things that don't fit, I'm going to shrink here. So what's happening when you parcel, when you shrink items by summing them together, the part that's being reduced is the degrees of freedom for the test statistic, because remember that comes from what the saturated model is, right? It's the number of unique terms in the variance covariance matrix of the data, right? So when you have, let's imagine you have 10 items and you're going to do a model for it, right? That has 10 times 11 divided by 2, 55 plus 10, 65 parameters, right? Now let's go along and say, so 65 parameters to it, and then you'd have 65 total possible parameters, and the degrees of freedom will be, the model minus that, and I don't want to go into what that is right now. I guess I could. Let's forget it. But then if you take 5 of those items and add them together, and so now you've got a model where you've got the original 5, and then maybe the 5 that you've summed together into one, you've got 6. So the total number of parameters in the saturated model for that is 6 times 7 divided by 2, 21 plus 7 is 28. So you go from, what did I say before, 65 to 28. So you all of a sudden shrunken all those places where the model may not fit well. And you've done it by a testable hypothesis that you never tested. Right? And so what happens is the smaller the degrees of freedom in your model statistic, the more likely it is you'll find good fit, because it's really close, things aren't being stretched out.
And you can rationalize that grouping, or I guess it would be rationalized by like a theoretical framework.
You could, but it's a
Right.
testable hypothesis is what I'm going with. Right? And so if you're going to go and say all these 5 will go well together, okay, test it. Do the model where you put all 10 in, and for those 5, make it parallel items.
So on that continuum that you showed us
Mhm.
one time, it's like we have the baseline model, we have our null hypothesis, and then we have the saturated
Mhm.
model. So this basically like shortens that saturated model.
Exactly,
side,
yeah.
but because you're not really getting like the full with
Exactly.
all the parameters, you're just kind of getting.
That's exactly it. And the other part that it does, which is really interesting to me, so to do the likelihood ratio test between models, like if you had the 10 item model versus the 6 with the with the ones parceled, you can't test the differences because they're not nested models. They're no longer nested because you've changed the data. Right? The nested models apply to the same data, the same people. Well, when you make that sum across the items, that didn't exist in the model before, so you can't compare the two unless you do a parallel items model on it. So if you put all 10 in but lock the factor loadings down for those and the unique variances down for those, then you can test it. And that's not likely to fit.
Oh, okay. Interesting.
Yeah, and actually I'll tell you this. The best it can do is fit as well as. And it's most likely, it can't fit better. It may fit as well as. But yeah, that's...
Yeah, because I was going reading manuals before, but when I came to Parcels, like I don't understand, so just moved on, and I did not even touch it. So
No, this is, to me, it's all about hiding fit. So.
interesting.
All right, well, we're actually almost done with the CFA part of the class. Can you believe it? One thing I wanted to show you was, what's that question?
I said, let's go back and do it all over again.
Oh, it's fine. You can relive the magic on the playlist on YouTube.
Just to confirm.
Yeah.
I think measurement and variance for the CFA, I'm not sure if we should because in the problem he mentioned
We're going to get to measure. We're going to have a whole section of the class on measurement variance. We're going to come up to that.
Okay.
Yeah, we're going to test whether or not, if you have a multiple group design, whether or not they're measuring different things or it's measuring the same. So one thing I wanted to talk about that you'll note is also one of the assumptions about CFA is the idea that your data are continuous. And one way that you can easily test that is this type of plot. I think I've shown you this before, where you plot the predicted responses, which is on the left, by each of the factor scores themselves. And again, that was that equation I drew for you for the regression line. The code that you see above it is a function I created that you can use to do the plot for you. All you need to do is call this CFA plots line after you've copied and pasted the function in, and it'll give you this plot for each of the factors that you have. What we're looking to see now, this plot right here, I believe is this the simulated? No, this is not the simulated. This is real data. You'll see that what you're looking for here, the dashed line represents the limits of your Likert scale. And this is sort of plus or minus however many standard deviations to the factor. Actually, no, this is outputting each person's factor score where their predicted value should be. Right? So I didn't even do plus or minus, just output each person's factor score, try to draw a line through it. And here what you see is that most of those people fall within the bounds of the Likert scale, and that's one rationale for saying this is mostly okay to use CFA on it. I still don't like that. These are still categorical responses, but that's what people will do, or what Lisa's done.
It's a little bit confusing though, isn't it? At least on the right one, that it's like out of bounds. Like how could a person get
Exactly.
0?
And so what you're going to find with a lot of the things that you do is that if you plot this, like most data is going to be out of bounds. And even then, what's also confusing about it is that this is a continuum. Like the -2 gives us a predict response on the 5th item somewhere around, actually, sorry, negative 1 here. That one right there is like 3.5. Well, what's a 3.5 Likert response? Right? You shouldn't see that. So.
It wouldn't make sense to anybody reading it.
No. It's a crude check, but it's fine. What else was I looking at here? Comparing sums or means. These are the means with the factor scores as well. You can see how that works. This is also this graph is sort of interesting here. This is if you take the sum score or the item mean, kind of the expected, instead of giving people a sum score, sometimes you give them a mean score. This is the bivariate plot of the positive function distribution versus the negative for the two factors. And here's what it looks like for the factor scores themselves. You'll note right here with this plot, you see this sharp edge on both of these? That's the ceiling effect of this test. There's also going to be a sharp edge on the floor as well. And that's because the idea that our factors are continuous and not our data are not continuous. So when they're not continuous, we impose a ceiling on the factor scores. And technically speaking, there may be another one as well if we use categories. Now, finally, if you take a look at the last section, this is an example write-up that Lisa wrote with respect to this. Bless you. I actually encoded all the numbers in this write-up using R, and then I put them in R Markdown. So I've been learning how to write papers in R Markdown. I know we're out of time, but let me just say this. If you do something like this and you have to change your analyses, so long as you have the code up here, the numbers that you see in the text down here come from that code above. They'll change too. And so if you wrote your paper in R Markdown, there's packages out there that will convert Markdown to APA style, like documents and stuff. Then you can encode your correct or the numbers that you want into the text below and have them automatically update for you, which I think is cool.
But you write the text?
That's right.
Okay.
So I wrote the text. No, yeah. Actually, I've seen people who've done that before. I've actually noticed there's a guy named David Kinney who developed an SPSS macro that wrote result sections for you.
Ooh.
So at that, okay, I'm going to stop the recording here, but basically at that, it's possible. I'd love to have a package that did that, but that's a discussion for another time. Stop the stream. There we go. Okay, so that's it for today and it for CFA. Any questions? I know I'm over time.